Hello, everyone, and welcome to this Transform 2021 tutorial put on by the Software Underground. If you're in the Slack chat, it is T21-Monday-Well-Data. Today, we have these three notebooks that we're going to go through. And at the end of each one, we're going to have a 5-minute break. The first one is the longest one. I'm guessing that will take 45 minutes or so. Just to get everyone on the same screen, this is the GitHub repo for this talk. And it should be below the YouTube live stream for this link. And you want to download, if you haven't already, you want to download this T21 Well Bonanza folder into your Google's Drive. This will have all the files and all the data that we need. Once you download that folder, so if you just go to I think code, you could download a zip. Once you download and unzip that folder and put it into your Google Drive, you should get something that looks like this. That's, I have it as T21 Well Bonanza. And if you look, it's right below my last year's talk. And so once you upload that folder into your Google Drive, it should look something like this. And again, if you're an experienced Anaconda or Python user, we're using very standard packages for plotting and other sorts of data analysis. So I'm sure any environment that you do have, we are going to install a couple packages like Welly and lasio and glob, but we do that within the notebook. So while, and then to get it started as well, we're going to start off with the 0_ca geotherm_data explorer. So if you're in your Google folder and you right click it, it should say open with Google Collaboratory. And that's what we're going to get started with here. Okay. So with some of you, that probably went a little quick. I'm happy to answer questions at the break of how to get started. But I would just feel free to follow along. And again, if you're already a Python pro, you can use this. These are just normal Jupyter notebooks, even though they're in Google Colab. So a little bit about me. I'm a PhD candidate at the Colorado School of Mines, the Chevron Center of Research Excellence Research Group. You can follow me on Twitter, and I'm working with Zane Job on machine learning stuff of core photos and well logs and other sort of subsurface data types. And then this notebook is going to be follow on from my last year's talk. And so if you haven't caught that already, there's the YouTube link and the GitHub repository is linked. And I highly recommend, if you've never worked with lasio or pandas data frames, that's definitely a great talk to check out. Nice to have prerequisites for this tutorial, but not necessary. If you've imported a CSV into pandas, made plots in Excel, MATLAB, Python, or R, and if you understand what a loop is, great. If not, don't worry about it. I want to give a shout out to Irene Wallace for geothermal context and some super helpful Python tips and hints. She has a talk coming up on this Thursday at Transform with Katie McLean on a deep dive at geothermal well performance. I've checked out her GitHub. It's super good. There's a lot of great geothermal insight in her talk, and there's a link to the schedule here. And so with this, I'm using geothermal data for all this viz work, but it's definitely not groundbreaking geothermal analysis. That will be Thursday afternoon. with Irene and Katie. Okay, now let's dive into the Python stuff. And so if you're using Google Colab, it already has matplotlib, but we're going to upgrade it because we're going to use some of the latest and greatest features. And in Google Colab, it's pretty easy to do. You can install it the same way as you install it on a normal Jupyter notebook using pip install, then the package name. And for us, we're just doing -- upgrade. And then you might get this warning to restart the runtime. And if you get this warning, I would definitely click it. It says you're going to lose some information, but since we haven't done, this is the first thing that we've done, we're not going to lose anything. Okay, and then now when we do this again, after the restart, it should say it's already up to date. Perfect. And so then another couple things we're going to import is pandas, numpy, date time, and glob. And we're going to get into glob later. And then this is how this folder is set up in my Google Drive. So it's just your normal Google Drive, my drive, and it's T21 Well Bonanza from the GitHub. But this might be a little bit different for you, or if you're running it from your Anaconda install. So this might need to be changed. But if you unzipped the folder from the GitHub repository and dragged and dropped it into your Google Drive, it should roughly be something that looks like this. And so we're just saying we're going to change directory. We're going to go into this folder with all our notebooks and data and everything else that we need. This isn't strictly Pythonic, the CD. It's because these notebooks have an IPython interpreter. And so it's kind of a neat sleight of hand to make that work. I'm not going to get into this today, but if you have any questions about why CD and PWD and pip install works in a notebook, feel free to drop them into the chat, and I'm going to answer those and look at those during our break. So let's look at all the Excel files, and within that folder, there's a ca_geothermal_data folder. Then I did star.xls. And so what I'm telling glob to do is make me a variable with all the Excel sheets that end in .xls and put them here. And so why this is nice, you can imagine globbing a bunch of PNGs, bunch of Excel files, bunch of CSVs. And so it's a great tool to search within a folder for one file type. And so with this, it's just imagine if you have a folder with 1,000 LAS files or 1,000 PNGs, you probably don't want to type out every one, especially if you remove a file or add a file. So glob is a really, really handy way to get all of these file names into a easy variable. Here, I'm not going to dive. This is definitely, if you show this to a CS professor, I bet most will whinge. But this is kind of how messy data extraction, data cleanup works. And so this is a loop from Z to range the length of Excel files. And so what I'm saying here, for every Excel file that we have, and so we have 5. And so we're going to print out the field name just as like a little QC. And then we're going to do some little individual sheet ways how to load it in, how to munge it, how to get to the columns that we actually want. And so with this, it's good to know that, yeah, so it's good to know that all these Excel files are a little bit different. And yeah, I'm not going to dive too deep into here, but we're going to just do run this cell. Oh, and it says name Excel files, not, so I must have not ran this. There we go. Let's try this again. There we go. Okay. So the field names needs to be fixed. And so this is Casa Diablo, which is here. This is Coso, which is further down. Then there's geysers, Heber, and Salton Sea. And so this is a little map that's provided from the California Geothermal Data web page. And so so geysers is the biggest geothermal field in the U.S. Casa Diablo is in Mammoth Lakes, which is a very awesome place to visit in the summer. And then we're going to look at Salton Sea and Heber, which is further to the south. And so now from that messy loop, we have this data frame underscore production. And so we're going to get a count of years, months, and then the production for every month for these geothermal wells is measured in metric tons. And so this is just a fair amount at the field scale. So this is a fair amount of water that they're pulling out of the ground, and also that they're pushing back into the ground. Just for some more QC, I just want to look at the month and just pull the unique variables of DF production. And so it looks pretty good, but let's sort it because I don't like counting from 1 to 12 and random odds and ends. And so if you sort it, it will line it all up, which is nice. And so having months range from 1 to 12 makes sense. We also have some data from early geysers that doesn't have a month because it just tracked the production yearly early in its life. And so geysers is a really special geothermal field. It's the biggest. It was one of the first. And there's a lot of history and lessons that the whole geothermal community has learned from the geysers field. And again, just to go to DF production, this year, month, production in metric tons, injection in metric tons, and then the field name. One thing I'm really interested in that we're going to explore is that there's a difference between the production and the injection. And so to think about reservoir pressure or subsurface conditions, these should be probably as close to equal as possible, but there's some atmospheric losses, just some general operational things. So that is not always the case. And so we're going to make a new column, which is just production minus injection. And so we do that here. And so we have the data frame name here, the name of our new column of pro underscore minus injection. And then we just have DF production minus DF injection. One other thing we need to do for date time is that it really wants a day. And so we have month in the year, but we don't have the day. And so with that, we need to make days 1. I made a flub. I just put days as 0, but there's no 0 day on the calendar. And so I highly recommend if you need to fudge a day for your own data analysis work, I would use 1 as the filler, not 0. And then with that, since we've added 2 new columns, let's just do a df.describe. And so now we see here's our old columns. We have production minus injection, and then we have day. One note here, I just noticed that the standard deviation of day is 0 because every day in this data frame is 1. So it's the min, the max, and then the standard deviation is 0. Okay, now let's get to the fun part. Now that we have matplotlib installed and our data frame cleaned up. And so matplotlib, it's one of the best plotting tools for Python. It's gained a lot of news lately because the helicopter on Mars, and the rover itself, the science team, they use matplotlib for a lot of their analysis, and so they were going through some of the pull requests on matplotlib, and you see a lot of @JPL email addresses, and so it's a really good, if you're going to be making plots and graphs in Python, matplotlib is really the kind of gold standard of places to start. Okay, perfect. And so if you just want a basic histogram, and so if you're really just doing the first exploration of your data, a histogram is a great way to go. So we're going to look at, in the df_production data frame, we're going to look at the production minus injection, and then we only care about the values of that. And just because it's a histogram, wanted to add a Y label of count. And so with that, we see most of them hover towards 0, but also look at it's 1e to the 6. And so even if you're getting up to 1 or 2 or 3, 4, that's a lot of missing subsurface mass. You also have some time where production minus injection is negative. It's below 0. And so while this is great that you can make, basically, if you took out the label, you can make a histogram with a one-liner, and you can start to think about these sorts of things. With matplotlib, everything is infinitely changeable. And so in this plot, we are going to look at production and injection separately, not the difference. And then in each line, so in this first line, we are setting the fig size as 8 inches wide by 4 inches tall. But if you wanted to go 8 by 2, you can make that change. So feel free to change these numbers. And then we're doing two histograms. The first one is production. The second one is injection. We're setting the number of bins. We're setting the color. And then alpha is the transparency of those colors, and we're giving it a label. The nice thing about giving it a label here is that when we call plt.legend, it will put the label that we put here into the legend automatically. And so feel free, when you rerun this or spend some time, to change the alpha. So as you can see, this is brighter green, less transparent. You can change the colors. You can change the number of bins. If you want to do one with 5 bins and one with 20 bins, you can make those changes. And so it's interesting when you change it to 5 bins versus 20, each bin has much more count. So this is kind of a funny way. I probably wouldn't recommend doing that. But again, you have total flexibility to change and alter this plot. So compared to this one, where all we did was do a one-liner of making the plot, we specified the number of bins, we specified the color, We added a legend. We set the opacity using alpha, and we also set the figure size. And all of these things you can change in your own plot. Another thing is here, there's a link to a paper here that I linked in my notebook. Reinjection in geothermal fields, a review of worldwide experience. So this was put out in 2011. If you're really interested in this missing mass problem in geothermal fields, I would check out this paper, and it is linked in the notebook. Like I said, I'm not a geothermal expert. I just think this is going to be a fun data set to cruise through. So another thing you probably want to look at using matplotlib is just a line plot. And just like before, if you only give it one thing, so df production, so this is our data frame, then we're just looking at production data and the values of that. And then the Y label is production in metric tons. It can give you this graph. But since this is the data frame for every well and every power plant, it doesn't really make a whole lot of sense because this x-axis is just count. And so this is good to confirm that there's data there, but I wouldn't really look at this for any trends. So let's look at just one geothermal field or one geothermal region. And so we're going to make a new data frame called Salton, and this is going to be just use the field name of Saltons. And so this is going to be a geothermal field in Southern California, right next to the Salton Sea. And so how this basically works is this is going to pull every time the field name equals Saltons, it's going to feed that to this outer DF production data frame, and then we're going to make a new one here. So let's run this cell, and then run this. Okay, awesome. And so the field name here is only one thing. There's still some funniness. And so we're going to make, instead of having it be month, year, day, all a separate columns, let's make a daytime column, and let's get rid of row 1. Since row 1 doesn't have any production, doesn't have any injection, we don't need to include this into our analysis. So this, we just made this little variable foo, and then we do Salton the columns of year, month, day, and then we can put this into pandas PD to date time, and use this foo variable that we just made, and we're going to make that a new column in our Salton's data frame. One way to QC these data frame is Salton.d types, and so this gets you all the types for all the columns. And so year is a float, month is a float, field name is an object. That makes sense. It could also be a string. But then date, this column that we just made, is a datetime object. And so one of the neat tricks that pandas does behind the scenes is make these datetime objects, and those are really slick. The other thing we're going to do, we're going to drop that first row, and then let's just QC the head of that data frame. Perfect. And so the first one that we start with is month 2 of 1982, and it all has sensible data with a nice datetime object. So from that simple line plot we had before, we can make, this is a big plot. This is, I set up as 20 by 7. So the second line is we're going to add a title, Salton Sea field production and injection history. Then on this plt.plot, for the x, we use the salton.date. That's our new datetime object that we just made. And then we're going to compare production and injection. We're going to make production green and injection blue. Gave these a label just like that we did with the bins. We did a Y label of metric tons of water. The other thing that we're going to look at is on the third line on the same figure is still using salton.date as the x, but we're going to look at salton production minus injection in gray. We're going to label that atmospheric loss. We're going to use a legend. And then because we use all these nice labels in our plt.plot, then we're going to do plt.grid, then axis y. And so axis y just means that you can set all this different ways to plot the grid. You could do X, you could do both, but I was more interested in the volume of water comparison than putting a line for every year. Since it's been since 2020 to 1985, I think having a line for every year would get a little messy, but you can definitely play with how often the lines show up, the X and the Y ticks. These graphs are infinitely changeable. And so this is just showing one quick way you can adjust this. Another way to look at it, instead of plotting this production minus injection as a separate line, matplotlib has this neat way you can fill between. And so you set up, you can do plt.fig size, still a title, but instead of plt.plot, you do fill between. And then you give it the X, the shared X, then you do production and injection. And you set the color, give it a label, and then when you run it, so everything that's filled in this green has, you can say like, oh yeah, if there's some missing, some water or, some atmospheric loss. The other thing that you can see, and it'd be awesome to see someone do this, they started in 1983, but they really didn't get going till the early 90s. And so it would be interesting to have a plot like this, then plot on top of it the number of wells for Salton Sea. The other thing I kind of noticed is that they have all these spikes that looks oddly seasonal. So let's take a look at that. So again, here we have plt.figure. So we set the fig size, we gave it a title, we have salton date and salton production. And unlike above, I just did a subset. So I just did from the 143rd index to the 200th index. So with that, because I didn't want to look at this early history or this late history, I just kind of wanted to look at what's in the middle. I did set the color, and then I set the difference to be also being gray. And so if you zoom into this plot, you can kind of see like, yeah, like there's this random seasonality or downward spikes you can kind of pick out in this yearly data. So it could be maintenance around winter. These geothermal wells, they get, because they're so hot and filled with brine and fluids, it's they need to be cleaned out a lot. It could also be when it's colder that these geothermal power plants are more efficient, so they don't need to pump as much water. And the other thing is, yeah, those are two big reasons why. So let's look at a scatter plot. And so if we just do a plt.scatter, so again, salton.month, because we're going to just only look at the seasonality of the Salton Sea data set, and then we have production on Y. I set the alpha, or the transparency, the 0.2 because there's a lot of overlapping data that's kind of hard to see. And this is for the entire data set. And then I just put an X and a Y label. In the first few years, like I said before, kind of have this lower band of production. So let's only look at the later bands. Perfect. Okay, so now we have, I set an X and a Y and a Z. And so the X is just the salt in month. Y is salt in production. And Z is salt in injection. I don't even think that we use Z. Oh, we use Z later. So while it's not used in this plot, it will be useful later down the line. I set the order to 5. This is for a polyfit. We're going to plot using numpy. So this first line here is the same scatter plot as you saw before. This plt.ylim just sets the y limits. This plt.label is just a label for the y-axis. And then here's kind of where a lot of stuff for this red line that was made. So we're going to make a plt.plot. So that's a line plot. But I only want the unique x's plotted. I don't want 1 through 12, 1 through 12, 1 through 12. I just want them done once. And then we're going to use np.poly1d and then np.polyfit to make a 5th order fit to this x and y that we set above for every np.unique x. And we're going to make that color red. And you can make this plot, and as you can see, the lowest on this 5th order fit is month 2 or 3. But probably 5th order is a bit much. I was just experimenting. You can use order 2. Order 1 would just be a flat line. You can do order 3, which still looks pretty good. Doesn't get as loopy. You can do order 17. Yeah, that doesn't make any sense. And so what's nice is that you can iterate through these and kind of pick your favorite. Again, I don't think the 5th order from a statistical point of view would be the most logical. I just kind of wanted one that looked good for this plotting exercise. But again, if you wanted to make a change or mess around with this, it's pretty easy to iterate really fast. Okay, now let's get to a bar chart. So again, this is going to be the same stuff as before, but just showing it in a bar chart. One thing that we're doing here is because we're fitting two bar charts into one figure, and you want them to share the y-axis, you have to make them into these subplots. And with this, we have ax.bar, so the plt.bar. And then another thing to kind of have these bars right next to each other is that you set this width as 0.25. And so then you have the x from above minus width over 2, and the same x as above plus the width over 2. So if you look at the bar chart, because they're months, you know, this is 1 minus width centers the bar, or width over 2, and then 1 plus the width over 2. And so even though for this kind of categorical months, it makes sense. So you can see production versus injection for each month, but without that little width trick, they will just plot on top of each other because they have the same months. And so then we have the x, normal y, normal z. So we use that z variable from above. Then you set the width of the bar. So if we wanted to change this instead of 0.25 to 0.5, you can get thicker bars. I bet if you go above this, they start to overlap. Maybe 0.35 is the right number for you. I kind of like some white space between it. I set the alpha really light, so if you see here, you can see that while the bottom of this bar chart is really solid in color because there's a lot of overlapping, you can kind of see in each one of these bars that there's only a few at the very top, and then as you go lower and lower down, it gets more and more solid color. So again, you can mess with this alpha just like we did with the histogram or a line plot. This is just setting some labels. This figure.type layout, this is kind of a nice trick if you're having issues showing and plotting these matplotlib objects. So if the plots are coming out a little odd, I would definitely give this figure.type layout a try. And so while this bar chart, it's true data, it's real data. I don't think it does that great of a job. I just kind of wanted to show off what is possible using a bar chart. A bar chart's not normally the first place that I go for plotting data, but I know that sometimes a decent bar chart is exactly what you need. Okay, new subplot magic. So about a week before this talk, there was a lot of chat on Twitter from matplotlib. They're a great follow on Twitter. Is that there's a new way to define subplots. And because subplotting in itself, if you want to have multiple plots on one figure, I've had to look it up every time. It's kind of tricky. It's not the most intuitive thing. And so with that, instead of saying, you can now define it. So for this subplot that we see down here, so it's 4 individual graphs onto one plot. You can use this new thing called subplot_mosaic. And then you give each plot a label. So we have bar, plot, history, and image. And then when you do this AX_dict, you can say for the bar plot, I want dot bar X and Y. And then for the plot, you can just do dot plot and it knows where to put it. It arranges it the same way that it's like here. And so if you're using subplots or have struggled with subplots before, I really recommend checking out the subplot mosaic. I'm not going to dig too deep into it here. I just blatantly borrowed it from the matplotlib Twitter handle not too long ago. And so I need to do a lot of investigation myself, but I'm very excited to see what's out there. And again, I don't think this is the best way to show off this data. I just want to give you an example of what you can do with subplots. Okay, now we're going to move from matplotlib to Seaborn. And Seaborn is kind of modeled after our ggplot. It's built on top of matplotlib, but it's a great way to show statistical type information without a ton of syntax. And so the first thing I'm going to show here is a violin plot. And this is something that I love using compared to a box plot, because it can show the distribution of the data within that. And so with this, I'm just setting the figure and the subplots, and then I have a violin plot of x equals x, y equals y. I set the palette, and I set the line width. I forgot what BW and cut equals. But that same seasonal data that we had from before where we fit the polyfit, you can actually look at the distribution instead of using alpha and having a bunch of data points stack on top of each other. So it's super nice. You can see like this month 3, there's a lot of outliers to the low end. And so using these violin plots, I find it easier to see the long tails usually on the lower end here, and that most of the data itself is pretty consistent. This is just to make sure that we know what our data frame looks like. We're going to use a set theme here. Oh yeah, this is a really awesome plot. So here, I'm just going to show the plot, and then we're going to go through what I did for each one. Okay, so this is our plot. So there's production for every year. So the y-axis is production in metric tons, and then it has the year up here. So then it has all the other years in gray. So if you're looking at a multi-year seasonal type data set, you can see that the first year, 1982, is definitely real low. And then as the field gets more and more wells drilled, more power plants coming online, the amount of produced water increases over time. But you can also see, that low period, month 2, month 3, month 4, they're either doing maintenance or there's extra cold that time of year. So it's kind of a neat way to investigate these multi-year seasonal trends. And I don't know why these only plot to 15. They only have 12 months. That might be something. If any of you out there have a great fix for that, it would be great. Okay, so with that nice plot, we are going to go through a lot of lines of how we made that. And so we're going to do G equals SNS. So SNS is how we imported Seaborn. Rel plot, and then the data is that Salton Sea data frame. X equals month, Y is production. Column is year, so we had each subplot for every year. And then the hue also year. This line width, order, column wrap height, this is just all different decorators for the plot. And then there's a little loop in here, or yeah, not a loop, but for year, comma. So for every year, the subplot in G dot, so this G plot that we just made, dot axis underscore dict items. So basically all the items in this axis dictionary that was made up here use all these same decorators and make a line plot. I wanted to reduce the frequency of the x-axis ticks, and then tweak supporting some other aspects of the plot. I set the axis labels, and then I did another type layout. So while this was very syntax heavy, I found this plot to be really cool to be looking at, kind of multi-year trends of the Salton Sea. Now, what you do with this as a geothermal subsurface engineer or geologist, I'm not really sure, but I thought it was a really neat way to show this multi-year data. And again, let's do a scatter plot. So using Seaborn, we're going to set theme. And so theme is just a way to set the colors and the grid and how it looks. We're going to set the figure size. We put a title here, and then the scatter plot here. X is just going to be Salton of production in metric tons. Y is Salton injection in metric tons. So the hue is the color, and so we have Salton dot production minus injection times 10,000. In size, Salton plus or dot production minus injection. So both the size and then I set the line width and the palette. So both the size and the color. So the closer it is to 0, so the closer it is to the injected water and the produced water being, 1-to-1 a perfect ratio. The darker and the smaller it is, and then the further it strays from that line, the lighter and the bigger that the dot gets. And why I picked 10,000 is if you, let's do just 100. You can still sort of see it, but I wanted something that, the size that would really pop. And so you can kind of play around with this to kind of see what makes sense for you, or even go bigger than 10,000. So scatter plot matrix, this is one of my favorite parts of Seaborn. This is a great way to explore your data and to see different comparisons and just kind of do some baseline exploratory work. So with that, we're going to make a new data frame. So I just did df_scatter for the scatter plot. And I have production, injection, and field name. So those are the only things that we're going to care about. And so we're going to make sns.setTheme. So for this, we're going to use the dark grid theme. sns.pairplot. So we're going to use that df.scatter data frame that we just used. The hue equals field name. And so this will split out each one of these colors based on field name. And then I set the alpha to 0.3 just to lighten it up a bit. So if we run this, so you see, yeah, it's kind of messy, but if you think that a lot of this data should sit, that where injection should match production, and then what's this green one? Oh, it's geysers. And so you see that geysers doesn't really match, and then this red Heber, which is in also Southern California, doesn't match. And then you can compare these KDEs of injection, and then you can compare these different names. It's a little spiky. I probably would want to expand on this and really, make this a bigger plot, or make these KDEs their own thing. But it's still it's a great way to look at a bunch of different data all on one plot. So in this quick talk, I've talked about themes. There's also, I put a link into the repository. There's this nice page here that goes over some of the theme options, and dark grid is just dark with a grid. And so if you want to explore different themes instead of you manually setting the background or anything, this is a great way to go. Also linked in here are 2 papers on Casa Diablo field and the Heber field. And again, with all this geothermal stuff, we've learned a whole lot. And so all the plots we've made so far have been static 2D plots. And then we're going to look at a super quick plot with Plotly Express. Now, Plotly Express isn't my first choice for doing super entry-level data exploration, but what it's really great for is interactivity or web apps. And I'm not a Dash pro. I know Michael Hardy on Software Underground, he had a talk a while back on making web apps with Dash. And so with this, I just want to make a quick, it's the same data that we've seen before, where X is the date, Y is production in megatons, and the hover name, you can set it what it is. And so this is the first line graph that we're going to do. I set the line color, and then I gave it a title for this overall graph. And then I did the same thing for the figure 2. So you have to make it, so you have to add trace. It's kind of messy how Plotly Express does this. If any of you in the Slack channel are Plotly Express Pro, I would love a way how to clean this up. But if we run this, So this looks like a normal line graph, but if you want to know what this lower spike is after 2010, we can get the injection number and then the date itself. Or if you want to know the production for that time, you can kind of scroll around and see both the date and then the number itself. And so Plotly is cool. You know, interactivity of graphs are great. You can modify these graphs in infinite ways. And you can even zoom in and zoom out. I've used Plotly a lot with trying to figure out like core to well log offsets or other sorts of things. So it's a great tool. Just know that the syntax here, I try to clean this up. It's a bit messy when you want to have a couple extra traces or multiple line graphs on the same plot. So if it's just for a report or something that's static, I would probably stick with matplotlib or Seaborn. If you want this to live somewhere on the web and want it to be interactive, definitely Plotly Express is something that I would look at. So some future research questions from this, since we're all geothermal pros. It'd be really nice to plot a lot of this data against number of wells drilled for each field, because this is on a field level. And the other thing it would be nice to look at is how the energy production from that field correlated or compared with produced water or injected water, or just wells drilled, and then how much energy these fields are making on a year-to-year basis would be great. That was kind of a blast through a lot of different viz stuff. And so there's some other links. Matplotlib has a great example web page. Same with Seaborn. And I know that there's people on Software Underground in the Viz channel that would love to help you with your plots. I just want to show what's possible in a couple lines of code to go from the basic standard matplotlib plots to something that's more, that fits your needs or that looks a little better. So with that, we're going to change this from a 5-minute break to a 10-minute break. And so we're going to see you hour 03, and then we're going to go into the next one, which is going to be well loading using Welly. And so there should be 1_well loading with Welly. And thank you so much. I'm going to hop in the chat if you're on the Software Underground, if you have any questions, comments, or thoughts. And if you weren't up to this, if you couldn't catch up with that last one, we're starting with a completely new notebook. So hopefully you can follow along on the next one. And with that, I will see you in 10 minutes. Okay, so I'm coming back from our little break there. Thank you so much. We have another minute till I'm officially going to start. And so we're going to be using, so last year's transform talk, I used lasio. This year I'm going to look at using Welly. Welly uses the lasio loading and exporting capabilities for well logs, but provides some higher level tools. And so with that, on this notebook one, I think we're going to get started rather quick here. But I will say, if you're in the Slack chat, I just saw the 15 months issue being fixed. And then some people had some issues with the field name that I'm going to be happy to go over and fix after this talk. And so with that, let's install lasio and Welly. If you're in a notebook and you've never installed this before, we can do pip install lasio and pip install Welly. Both of these I've had a fair amount of changes and in improvements in the past couple of weeks. I think there's a little lasio hackathon going on with Transform, and it's just been awesome to see. Both of these packages are one of my favorite packages to use. And so we're going to import lasio and Welly, also pandas and numpy. One thing I kind of like to do is to print out the versions. And so with the Welly version, there's been some changes that I've really liked to see, and same with lasio. So this is a good way to make sure that you're using the latest and greatest version. The GitHub is here for Welly. I put a link to it, but the other nice thing is to read the docs. And so it has really good documentation. And so if you have a question about Welly or lasio, I highly recommend checking out both things. There's also a Welly and lasio Slack channel on the Software Underground, and there's a fair amount of troubleshooting, fixing, and just sharing of ideas and workflows. And so just like last time, need to make sure that I think I'm already there. And so if you're in a notebook, you can also do pwd. Yep, and so I'm already in that folder of t21_well bonanza. Okay, and so if we look inside t21 well bonanza, there's this folder of kgs_2014_modified. And so this is just a folder filled with LAS files. And so I'm sure everyone here has folders and folders and folders of LAS files and varying organization. And so with that, we're from Welly, we're going to use the project. And then the other thing that we're going to do, we're going to alias these well log curves. There's a couple different aliasing well log curve packages out there on GitHub. Jesse Pizzell has a really sharp one that uses PyTorch, fuzzy logic, definitely some higher level tools, and these Welly defaults to make these well log aliases. We're going to use this a bit lower down in the notebook, but we're going to look at well quality, and we can kind of define that, what that means. But we're going to import that as Q. Now, it doesn't really make sense to call this TED. I just wanted something that was memorable and wasn't, named alias, but obviously TED might not make the most sense. So this is a direct link to the defaults. And a lot of these defaults are from Crane, Spec 2000. And so if you look at GR, he ranks them relatively. And so for me, when I'm looking at a whole folder of wells, I'm not too picky if it's a GRC versus a GR versus a GRN. I'm not a petrophysicist, and so I'm just interested in what a gamma ray log is. But I know these differences do mean something. So while it might make sense for a big machine learning project with hundreds of wells, if you're doing a one well petrophysics project, I probably wouldn't alias them all. Then you can kind of scroll through TED here as well. Okay, so one nice thing about Welly is that we're going to make this project P. So project.fromLas, and then we're going to give it a link. So within this kgs_2014_modified folder, we're going to feed this Welly project every .las, so star.las, that's in that folder. And so if you have a bunch of well logs in folders, this is a great way to kind of search through. and pull all the .les files from one folder. And the loading of lasio isn't super fast. I know that's one of the things that they're working on in the hackathon this weekend. They're looking at using a pandas base, which early results are twice as fast. I've done this with up to 500 wells. I know some people on the Slack have done thousands of wells using Welly. I would personally budget 1 to 2 seconds per well of load time. And so if you have, every well from the North Sea or every well from Texas, that could definitely take some time to load. If you're an R user, there's a R well log loader, which is exceptionally fast. I'm going to say it's 10 times faster than lasio, but you lose a lot of the header information. So it's really good at getting the data from the curves, but it's not. You do lose some header information and other stuff. And I will drop that into the Slack. Okay, so now that we have this project P, and if you run this, you can see you have the index of the wells. So we loaded in 23 wells, or probably 24, yep, because the index is at 0. It will tell you what curves are in the wells. It gives you the UWI. Not every well has a UWI. And then the other nice thing that it will tell you the names of the curves. So as you see here, there's a lot of really specific curves, like RT60, RT90 instead of deep resistivity. And so we're going to alias these to kind of get a more functional data frame. The other way you can load it into a project, which I've also done, so this is our old friend Glob, like we used in the previous one, is that we're going to get a list of files. So it's in the same location. And then instead of UWI, we're going to use API. There's still some missing APIs, but we're going to load these wells, and instead of it's going to still show up as UWI, but it's really the API number. The other thing, these are wells from Kansas, from KGS, and so we're going to set the index to feet, and we're going to remap the UWI here. So that's going to run. So again, it's still making a Welly project, but it's loading it from this wells object. Unlike doing it from above, it doesn't really give a status check on what well it's on. Then if we show this project, it still says UWI, but more of the wells have an API. So again, it's not perfect, but it still shows the index, the data, and the specific curves. So these are 2 ways to load in to make a Welly project. I'm sure there's other ways you can do it. There's pros and cons to both. They roughly take the same amount of time. It just kind of just depends on what you're looking for. I kind of like this remap of remapping API to UWI. That makes sense to me, but it might not make sense for your specific project. The other new thing in Welly that's been nice is that you can set the index. So for this, I think all these wells are in feet. They're all from Kansas. But if you have a mixed folder of wells with some metric and some US wells, or even I've seen some weird footages on the North Sea, and I've seen some pull requests on lasio to read in like fractional inches. And so there's all these, you can almost find a LAS file of any flavor of depth index. And if you want to have them all on the same depth index, this is a great way to get it there. And again, I know feet's kind of a goofy thing, but since these are Kansas wells, we're just going to stick with feet. But you can make this whatever index that you want. And that's a relatively new feature into Welly, which is pretty nice. Okay, and so even though the whole point of Welly is to look at multiple wells, let's just look at one well. And so in this Welly project of Proj, P-R-O-J, let's look at index 4. And so with that, you can get the well name, you can get the UWI, you can get the state, the county, section range, township, API, and then the data name. So this is a great way if you, as you're exploring your data and looking at your folder of wells, this is a great way to kind of quickly scroll through and get some of this header information. And if you want the header itself, you can just use, so this is the Welly project, the index of the well dot header, then we'll spit out all the things here if you'd prefer a dictionary of it. So you could see making either a function or a loop and dumping all this header information that you have in a Welly project into a separate big dictionary. The other thing you can do with one well or a lot of wells and compare it is you can make a plot of every curve that it has. Now these wells I pulled from KGS, they kind of have a lot of data, but you can kind of get at least a quick QC of where this, like, this decal, so this lower caliper, so they probably ran a separate set of tools for the reservoir, interval down low, and then you have this complete gamma ray. And so if you're wondering why you can't do GR cross plot your decal, doesn't make any sense in the shallow section, yeah, because this data is a perfectly flat line. Or this conductivity log, there's this big spike here. Maybe that's something that you want to investigate. Also, this RILD and RILM data is real spiky if you look at the units here. So again, this isn't meant to be your last plot or your only plot. This is just a way that you can quickly kind of look at a high level and start to QC what curves you have, what's going on, what you want to cross plot, and so on and so forth. One nice thing too in Welly is that if you want to export one of these as a new LAS file, even though as you have it in a folder within the Welly project, you can do .toLast and then just get a name of project 4. So I'm just using the 4th index of proj.last. And so this is a great way if you think of when we loaded these in, we set the foot or the depth in the Welly project. And so if you want to go through and make changes like that, it's a really nice way to kind of go through and bulk export .las files, or if you make any other changes to the projects. And so if you do proj, so this is still just the Welly object.df, you will make it into a data frame. And then let's check out this df original data frame. And so it's 231159 rows times 120 columns. And so it's a dual indexed data frame. So both the UWI and then the depth. Then it has every curve that's in your data set. Yeah, so RT90, RT60, RT30 instead of like a deep or shallow resistivity. And so for me, again, I'm not a specific petrophysicist, but I prefer to have an alias data frame. And so let's make a new df_alias. So in the project.df, you can feed it keys, and then you say alias equals TED. And so TED is that alias list that we loaded from above. And then just for this demo, we're going to drop all rows with 7 nands just for this demo. I'm not saying that makes sense, but it'll be just a nice way to look at a fairly full data frame. And then let's just check out the top 10 rows from this new DF alias that we did. And so if you look here, it still has, dual index of U, WI, and depth. Then it has your caliper, gamma ray, SP, density, deep resistivity, photoelectric factor, neutron density, neutron porosity, and then it has this DT, the sonic log, but for this, it's mostly nans, or all nans in this head. And so this is the type of data frame that I typically start my analysis with, is that you have a well, a depth, and then an alias data frame. If we want to make a new curve, now that things are in a data frame, this is a way to do it. So again, we're going to use this df_alias. We're going to make a gamma ray times sonic log. So then we use df_alias dot gamma ray dot values times df.alias times dt times values, or you can do any formula that you like. If you think gamma ray minus dt, or whatever sort of petrophysical transforms that makes sense to you. I'm not saying gamma ray times dt is the secret to everything subsurface, but it's a nice, this is an easy way to do quick petrophysics on a lot of different wells. And with this, we can't really see anything because there's no dt, but let's do df_alias.describe. And then if we scroll all the way over, you can look at the top count, which is just a little bit less than dt. And so we did make some data, it just isn't showing up in this specific output here, but it does exist. And yeah, I even made an histogram to prove it to myself that this thing is real. One nice thing too, using the same alias as before, you can write out to an HTML table. Then you can see, so out of these 24 wells, all of them have gamma ray. 21 out of 24 of them have row B, 23 out of 24 of them have SP. And then as you get further down the line, it has less and less. But this is a great way if you just want to do a visual QC of hundreds of wells in a folder, and you want to know, can I do a sonic log analysis, and only 3 out of 300 wells have a sonic log? You might want to look at something else. Or maybe 297 out of 300 wells have a sonic log. So great, let's do some sonic log analysis. So this is a really good way to visualize curves, curve names that are in your data set. And with that, we're going to do some well quality. This is blatantly borrowed from the Welly tutorial. But let's say for gamma ray, that we want nothing monotonic, nothing flat, and all positive. If that's your green light, red light, yellow light of gamma ray, those are some rules we can have. And then for your sonic log, we want it to be all positive and then all between 50 and 200. Again, you can change this to whatever you like. And then now when you look at gamma ray in your sonic log, you can get some green dots and some yellow dots. So if you want to QC a whole folder and look at how many wells are all green, how many wells have yellow dots, how many wells have this many curves, it's a great way to kind of scroll through and get a handle on what curves are in your data set. And again, these rules might not be good for you. You can write your own rules for each curve if you want. One thing that kind of comes to mind is like if PE, photoelectric factor, is above 8, I would probably flag some of that data. Or if it's above 10, it's worth a second look. or if one thing that can sometimes need to be processed out is like some of the porosity logs. Is it going from 0 to 1 or 0 to 100? So these are just the sorts of things that you can kind of look at in a nice HTML table. And so while it's a bit unwieldy for 24, it's definitely easier than if you have a whole bunch. So the last thing we're going to end on, I know that we just did a bunch of cross plotting, but this is the photoelectric factor versus the gamma ray cross plot, where I used a very low alpha. There's a bunch of overlapping data. So if you want to come up with petrophysical cross plots for your whole folder or your whole basin, or look at multi-well plotting or cross plot analysis, you can do that pretty easily. I'm not saying that this one makes a lot of sense, but to go from your aliased data frame to a plot, it's pretty easy to have multi-well data. So I think this is really awesome. This is something that I use it a lot for. This plot doesn't look that great, but with those skills you picked up in the first notebook, I'm sure you can make all the cross plots and line plots to your heart's desires. And so just as a quick overview of Welly, again, if you're not familiar with well logs or lasio, which is the reader and writer, I would definitely check out my Transform 2020 talk. It really goes over how lasio works, but Welly is great if you have folders of wells. If you have 10, 15, 500 wells that you want to do analysis and petrophysics on, Welly is really the tool that I would look at. If you're looking to do one well plots or one well petrophysics, me personally, you can start off with Welly. There's no reason you can't, but I probably would stick with using lasio. But again, if you have comments or suggestions or use cases, feel free to drop it in the Slack channel or into the lasio and Welly Slack channel. We're going to stop here for a quick 5-minute break. So at it's 3:31 Denver time, but probably hour 31 worldwide time. And then we will pick up with a neat slider bar decline curve in Python. And so with that, see y'all at hour 31. All right, coming back from the break, I know this is the last talk for the day, a transform. You're so close, you're almost there. This last one will be real quick. One thing that I did a major overlook, and I do apologize for, make sure that you're mounted to your drive. And so you need to give Google explicit permission to look through your drive. And so here on the right-hand side, there's the table of contents. You can do a find and replace. There's some code snippets you can add in. But on this folder one, you click on full folder. There's this folder with the little Google Drive icon here. You click Mount Drive. You're going to need to permit this notebook to give access to your Google Drive files, and you're going to say yes. So again, I do apologize for not getting to that the first time around. Okay, so we're going to make a fun little slider bar decline curve. And then make sure you're in your content drive, my drive T21 well bonanza. You can do a ls to list everything that's inside here. And so we're going to load in this CSV that should be in the folder, and then we're going to change the column names using the df.rename function, and then we're just going to look at the top 5 rows. And again, this has just month, year, oil, gas, and water in barrels, and then days that they sampled it. This is going to be a pretty quick and dirty way. We're just going to use the index. So each entry, this is only for one well. For each entry, it's for the month. And so I'm not keeping track of if it was sampled at the end of the month or the beginning of the month. And this isn't even a great decline curve, but I just wanted to show what's possible using Google Colab. And so with that, this is just a normal matplotlib figure. There's a big spike, and then as you can see, the barrels per month of oil, it declines and basically flat lines. This is a gas well, I think, in southwestern Wyoming. And so these numbers of oil production isn't going to be life-changing to anyone, but I think it was drilled in the time of $8 gas, which is definitely quite a ways away from today. Okay, and so if you want to give this to a colleague or a manager, you can hide a whole bunch of code. So if you right-click here, you can do form, you can do show code, or hide form, or add a form field. This is kind of a Google Colab interactivity thing. And so let's do oil decline curve from month 1 to month 250. And then if you press the run, it will give you a number of months. It will, this is fluid type and gas, so it's in red. And then it will plot the data, and then it will plot the fit in this black dashed line. I just use scipy fit curve. This is no way investment advice or how anyone should really build a decline curve, but it's just a one-line function. And then if that's too far out, you only care about the short bit, you can kind of play around with these sliders. Some of them don't work. Again, this is kind of a fun thing that you have to mess around with, and some months work better than others. Like this, yeah, this oil one looks good, but again, this is a gas well, not an oil well, so you definitely see a bunch of production dropping out. And then the fit function is definitely a bit screwy if you've definitely done decline curve analysis yourself. And so with that, let's go right-click it. Let's go to form. Let's go to show code. Okay, so there's a whole bunch of syntax. Here, let me make this a bit bigger. There's a whole bunch of syntax hidden in here. And so you have your slider. So this ended at 2 and 256. And so those variables are stored here. Fluid type is a variable, so our only options are oil, gas, and water on the drop down here. If you had a fourth fluid type like NGLs or whatever else you want to do, obviously you can change this. I also made it so if you made the minimum month greater than the maximum month, we scroll down past, it spits out error, check min and max month. There's obviously a lot smarter ways. You can probably set something to that. And then I made a little model function of just a little exponential curve here. You can set the figure size and the DPI. And then I just did a if or elif statement. If fluid type is oil, plot this from the minimum month slider to the maximum month slider. I set the semi-log y because it's exponential decline, and then you do the same thing for gas and water. And I know I did water is blue, I want to say, but here, let's put this back towards 1. Run this here. Yep, water is blue. And then another if elif statement for Y limits and Y labels. Because it's MCF per month and barrels per month, so each fluid has its own label type. And yeah, so this is kind of just a fun, if you have a little widget that you want to be interactive in a notebook, this is a fun way to do it. The spit function, again, is a one-liner from scipy. Again, it's not what I would use professionally for decline curve analysis, but again, you can use this notebook and fill in the code and what your secret sauce to do kind of decline curve analysis. The other thing that's nice that I like sharing with this, if you right-click, click on form, you can do hide code. And so while a lot of that syntax might be overwhelming for some people, you can definitely hide it behind the plot and just have them mess around with the fun bits of figuring out what slider bar numbers work and what slider bar numbers don't work, and what the fit function works. So like on this one, it spits out this optimize warning, and you can see it's just this flat line. It didn't really do what it needed to do. I know if you extend the months out a bit, it definitely looks a little better. So again, this isn't the smartest decline curve tool. I just wanted to show how you can kind of make a somewhat interactive plot. So the plot isn't like Plotly, where you know what the individual data points are, but you can kind of mess with what fluid and what month window you want to look at. And with that, that's really it. We're at the end of the road. If anyone has any questions, comments, or thoughts, please hop on the Slack channel. I'll be on for a little bit, helping people working through all of this. I will say, if there's a lot of great transform talks for the rest of the week, birds of a feather, everything on Wednesday, some lightning talks on Friday. And so definitely hop on the transform schedule, check that all out. And thanks to today for walking through all of this. This GitHub is below the YouTube video. If you have any pull requests or questions, you can reach out there. I'm on Twitter, and my email is also on the notebooks. Well, thanks so much. And I hope to see everyone on the Software Underground Slack, and I hope to see everyone at more talks. So thanks again, and see you around.